Let's take a look at what happens when we do some tensile testing. So as you saw in class, we're going to use this machine to pull apart this object right here. So this object that I'm pointing to right now is right over here in this picture. We've taken a quarter 20 threaded rod, so that's 1/4 inch diameter, 20 threads per inch. And on the mini lathe, we've removed material until we have this roughly circular cross-section region here. And we measured its diameter at 0.092 inches, so 92 thousandths of an inch. And also we measured its length at about 0.503 inches. So we're going to pull this apart. So this piece here and this piece here are really in there with the threads, and it's just going to go in opposite directions, and it's going to break, as we saw. So when that happens, we should get a curve that looks something like this when we plot the stress versus the strain. Remember, the stress is when we take the force that's applied to pull this thing apart, and we normalize it to the area, cross-sectional area of the sample, because we're not interested in the shape of the object. We want to get that out of the whole discussion. We are just curious about the material's property of the steel, or in this case it was aluminum. So again, we normalize the force by its cross-sectional area of the sample, and we get the stress. So it's called sigma, force per unit area, and units are either newtons per square meter or Pascal, or psi, pounds per square inch, which is what we'll be using. And then the strain, recall, is the amount of elongation divided by the original length of the sample. You can imagine that a really long sample is going to elongate more than a really short one, because there are just more chemical bonds along the axis that can distort a little bit, so you're going to have more elongation with a longer rod. So again, we normalize the elongation. When we pull it apart and it starts to behave like taffy, we normalize that to the original length. So we're plotting stress versus strain, and everywhere you see blue here, this is where it's acting like a spring. So we start to increase the stress. Remember, stress is almost a synonym for force. And we increase the stress, and the strain, which is almost a synonym for the elongation of the object, increases proportionately at some level. So we go along the straight line, the slope of which is our friend the modulus of elasticity, and we come up here and we get to the point where we stop being proportional. It starts to bend over, as you can see right here on the graph, and then at some point, a little bit past that, it starts to behave like taffy. So if we get past this yield point, then we're kind of in trouble. It hasn't broken yet, but it's no longer going to snap back to its original shape. Whereas if we stay in the blue area here, as soon as we remove the stress, the material is going to come back to its original shape. But once we get in the pink area, then it's going to start to behave like taffy. And so as we continue to apply stress, we get a great big jump in the strain, and then it does this sort of behavior. Again, we're not adding that much stress or force, but we're getting a lot of elongation. So it's like taffy right here, and we get up to the maximum stress that it can take, and then it eventually does this, and boink, it fails right here. It snaps apart. So this is a curve we're going to generate with our data, and we're going to use not Excel, but Google Sheets to analyze and extract some of these quantities, analyze this curve and extract some of these quantities. So let's begin that. First, I want to do a brief digression with respect to using spreadsheets. Spreadsheets can be your friend. There's fancier software for us STEM people, but you should always know how to use a spreadsheet because they're everywhere, and you can get a lot of use out of them. So I'm going to plot this formula, y is equal to ax squared. And in particular, I'm going to choose a value of a of 5. So I'm going to plot y is equal to 5x squared. We all know what this looks like. It's going to be a parabola. But how would I graph that easily in Excel? Not Excel, in a spreadsheet. Well, I'm going to use a combination of absolute references and relative references. So the relative references are going to make it easier for me to just key in one formula and then drag down for other numbers, and it's going to update for me, so it knows what I want to do. However, there's some cases where I don't want that to happen, and that's an absolute reference. So right here, I've put a is equal to 5. So in cell F2, we have the value of 5. So I want to reference that. So what I'm going to do is just say equals, and I want 5 here. So I'm going to click in F2. You can see it's F2 in the formula there. And if I hit F4, it turns it into a relative reference. A relative reference can be identified because it has a dollar sign in front of the F or the column and a dollar sign in front of the 2 or the row. Now if you're not on Windows, F4 I don't think works, so you'll just have to regularly key it in. So that is always going to be the number 5. Now I'm going to multiply that with asterisk, which is the multiply sign, and then my x value is over here in A2. So I'm going to click x, and now I'm going to square it, so that raises it, so the caret 2, that's going to make 5 times 1 squared. And I've got a relative reference pointing at the 1 and an absolute reference pointing at the 5 in cell F2. So if I hit enter, I get the right answer. And if I click on the cell, you can see I've got my formula there. But now I want to know what it is for all these numbers as well. So I could key it in, just the same formula over and over again, but that's the point of relative references. I can just drag this down, and the spreadsheet's gonna update all the relative references. You can see this is no longer A2 over here for the relative reference. It's okay. It was A2, now it's A3, now it's A4, A5, A6, A7, but notice that the $F, $2 doesn't change. That's an absolute reference. Okay, so we're going to be using both of these for our analysis, so I wanted to make sure that you all were aware of that, the difference between absolute and relative references. So we could come in here, we don't have to do this actually. Well, I won't mess with that, but you can see we've got it graphed and it is correct. So that's that. Okay, let's now go to the data. So this is the data that will come straight to you from the experiment. And so I always make a duplicate of my original data and just leave it alone. You can even hide it to get it out of the way. And I'm going to work on this copy. Now I can get rid of all this stuff here. Delete rows. And what I want to do, right now I've got displacement versus and force here. So displacement is the amount of extension. Force is the force applied by the machine. So I don't want that. I want stress and strain. So let's go here and let's clean up the data. So if I just grab this and plot it. So I'm going to grab the data, insert, chart. You can see I'm going to get something that looks like the curve we want to have, but it's over here on the right. So I'm going to go ahead and delete all these zeros. So let me delete this chart. And actually by deleting the zeros, that's going to make, or the ones, this is after it has broken. Let's delete all this. It's going to, let's see how what it makes our, by the way, did you know you can grab here and you can pull that down and therefore you can scroll and still get the header. So I'm just going to grab A and B, insert chart. Yeah, and that's kind of what I want right there. That's my graph. So I'm going to compare this data to this, or that chart to this chart, and I'm going to extract the information using the spreadsheet. Okay, let's leave it there. But again, that's not really the force that the graph that we want. So I'm going to just leave it there, put it aside though. What I want to do is I want to have stress and strain. So here's where I'm going to use the absolute and relative references. So displacement will be on the horizontal axis, or it is now, and we want strain to be there. So let's go ahead and put strain. Strain is dimensionless. Sometimes it's useful to have the header be a little different in appearance. Strain is dimensionless, and here I'm going to have stress. And that's going to be in PSI. So I can grab C and D and double click right there, and I can get it to show the text. I'm going to separate them by a little column there. Okay, now for the strain, I need to define the displacement, which is the elongation divided by the original length. So let's go ahead and put in the original length. We don't need this chart anymore for now. So I'm going to put here about under H. So this is original length. I think we've been calling that L0. So there it is. And I'm going to put its value right here, 0.503 inches. And let's see, over here, I'm going to say this is the diameter of the, this will be in inches. And this should be also in inches. So let's grab these, double click here, we can make it big enough. Okay, why don't we make the center justify so it looks better. Diameter was 0.092 inches. Okay, well, let's put the area here, the cross-sectional area. We'll just put area, and that's going to be in inches squared. Here, here, here. And so this is going to be equals, I think I can say pi r squared times, but that's the diameter squared, so I'm going to click over here, J2 divided by 2, and then I need to raise that to the power 2, so that's pi r squared. So I get that many square inches. Okay, is that right? Pi times the radius, which is half the diameter, squared. I think that's right. Okay, so let's go ahead and make the strain here. So this is going to be, the strain is going to be equal, remember this value, divided by the original length, which is here, and that's going to be an absolute reference. So I'm going to click here, press F4, and then I think I can just double click. Well, I can move down here and it's going to update. I think it's because I'm not directly adjacent to the other numbers. It doesn't allow me to just double click there. Okay, so these are the strain values. And again, this is a dimensionless number. This is the amount of elongation divided by the original length of 0.503 inches. Now the stress, that's going to be the force, equals this force divided by this area over here. Click F4. And that's a absolute reference. Okay, so I click there. There we go. So it anticipates what I want to do, and it gives it to me there. So this is my data. I've got the stress and the strain. So I'm going to grab these two, insert chart, and there's my chart. And so I have a little bit of room. I'm going to move to its own sheet, and there's our chart. So what are the things we can find here? Well, we can get the ultimate tensile stress. So we can come up here and find the maximum value. We can find the maximum extension. It looks to be about 18% of stress, of elongation, right? 0.15, so this is 0.20 is down here somewhere. We can get the slope right here. That's going to give us the modulus of elasticity. And also we can find roughly where it starts to become like taffy and plastic, yield point over here. So we're going to do that in the next video. Thanks for watching.